All right, this is Unit 5, Lesson 4, Graphing. And in this particular lesson, we're going to go over 4 new parent functions. Okay, y equals square root of x, y equals x squared. These two are inverses of each other. And then we're going to do y equals cube root of x and y equals x cubed. Similarly, these two are inverses of each other. So the first part is going to be our parent functions. The second part is going to be finding intersections. The third part is going to be writing equations given a graph. And the fourth part is going to be transformations and extensions. Our first parent function is going to be the square root of x, and we are going to use our transformations to graph this. So we're going to write down a couple things. Our starting point is going to be 0, 0, and that's actually going to be a point. Okay? Our a value is still going to be the stretch or reflect over the x-axis, okay? And our h and k are still going to be our starting point, which is actually connected to our 0, 0. After we graph the initial function, we'll put up a few more characteristics. So let's go ahead and fill out the table. Plug in 0. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. And then plot the points on the graph here. Okay? And then connect this in a smooth, curved line. This point right here is the starting point, and that is an end point. And then the arrow only goes on one end. So if we're looking at our domain and range, we're going to start at x equals 0, included bracket, and we're going to end at positive infinity. For the range, okay, we're looking at the y coordinates. We start at 0, and we end at positive infinity. Okay, keep in mind that our h coordinate is opposite, and it goes right and left, and our k is up or down. And then our a is a reflect or stretch. So let's look at some other characteristics of our graph to see if we can pick out what we're doing here. Okay, so we have an endpoint and one arrow. We have restricted domain and range. And then let's look at how do you actually graph this. Okay, so if I start at the beginning, okay, so I'm not going to label this the vertex, but I am going to label it the starting point. Okay, so let's look at our next point. Over 1, up 1. And so if we look at our table in terms of change in x, change in y. Okay, 0, 0 is the start. Our next point is over 1, up 1. The next point from the start, over 4, up 2. The next point is over 9, up 3. You are not memorizing where to put these points. You are reasoning out where they go. Okay, so change in x and square root the change in x because this is the square root function. Okay, so let's go and figure out what our review parent function is. X squared. Okay, now I only gave you 0, 1, 2, and 3, so I'm going to go ahead and put plus or minus here. Notice that the output values are the same. Let's go ahead and plot our points. And draw. Okay, so in this particular case, we have a vertex. And here it's 0, 0, but it is also HK. A is still going to be our stretch or reflect over X. Okay. The exact same things apply for A, H, and K here as they did above. So looking at my graph, my domain is all real numbers, and my range starts at y equals 0 and goes all the way up to y equals positive infinity. Now, if I look at my points, we're going to look at the points in terms of the comparison to the starting point, or in this case, the vertex. Okay? If I go over 1, I go up 1 squared. Why do we square it? This is the square parent function. So if I go over 2, I go up 2 squared. If I go over 3, I go up 3 squared in order to get to the y coordinate. Okay, so let's do the third parent function. This should feel very repetitive because the same quantities and the same characteristics apply. So instead of having a vertex, we're going to call this the center, and it's going to be HK, and it's still coming from these coordinates right here. So A is still our stretch or reflect. H is still opposite, and it moves right and left. And K is up or down. All right, so let's go ahead and plug this in. So we have the cube root. Cube root of -8 is -2. Remember, negatives stay negative for cube or odd roots. Cube root of -1 is -1, 0, 1, and 2. So let's go ahead and plot these points. Oop. Whoops. Okay. 2, 4, 6, 8, 2. Okay. 2, 4, 6, 8. Okay. And connect with a smooth line. Okay, so I'm going to do this in 2 parts. Okay, there's the top half. And here's the bottom half. And we have arrows on both ends. So if I'm looking at domain and range, left arrow to right arrow, negative infinity to positive infinity. Now this arrow, although looks horizontal, is actually pointing down because this keeps going down and down and down, but just very slowly. And so my range, negative infinity, this arrow keeps going up and up and up, but slowly, so to positive infinity. So let's look at our graph and see if we can write down some characteristics. In this particular one, we have arrows, both directions. Okay. The cube root looks very flat. Okay. It flattens out as the graph keeps going here. Okay. And then let's look at our table. Change in X, change in Y. Okay, so let's see. I put -8. And if I go over 2, 4, 6, 8, I go down 2. Cube root. Why am I going down 2? Because what I'm really doing is I'm cube rooting that distance from the center. Everything counts from the center. -1. Down 1. +1. Up 1. positive 8 up 2. One other characteristic I notice is that this is a positive 1 in front. Okay, look at your center 3 dots. They look like a 1 slope for the middle 3 dots. Notice my A value is positive, and it looks like a positive slope. All right, so let's go ahead and do our last parent function, x cubed. You should be able to do this one without any assistance. Go ahead and try. Connect in a smooth way. Okay, so again, let's write out some characteristics to help us recognize this graph. So the center is HK, which in this particular one is 0, 0. There's my center. Okay. It has 2 arrows in both directions, which means that my domain and range, okay, this one looks tall. So now we're doing similarities and differences. The cube root is very flat. The cube is very tall. Notice that the center 3 dots are the same on both graphs. The only way to tell them apart is to look at the next dot. 8, 2, 2, 8. The cube one is taller because you're cubing your input, which makes it bigger or taller. Okay, so let's keep filling this out. Okay, now our A, H, and K do exactly the same thing as they do before. Okay, so let's write down our table. Change in X, change in Y. So if I start at the center, notice that these are very symmetric, not quite like the parabola. They're symmetric over the origin here, okay? But you can still use the count values to do this. So 1, 1, 2, 2, 4, 6, 8. And then the plus and minuses carry over. Remember, cubing a negative stays negative. Cube rooting a negative also stays negative. 2, 2, 4, 6, 8. All right, let's go ahead and do a few practice problems. Let's start with one of our newer parents, and we're going to put in all 3 transformations. Negative 1/2 x minus 2 cubed plus 4. Okay, so let's start with the transformations. Stretch by 1/2 and reflect. Reflect over x. Compress 1/2. Right 2, remember it's opposite, up 4. And so my starting point, this is going to be your center, right? Because we're coming from the parent x cubed. Okay, right 2, up 1, 2, 3, 4. Okay, so I'm going to write down my table of values here, right? Change in x, change in y, and I'm cubing 0, 0, 1, 1, 2, 8. You can write 327, but 27 is so large it rarely fits on our graph. Even if I half this, 13.5, it's unlikely to fit on my grid here. Okay, keep in mind, cubings, negatives stay negative, positives stay positive. Okay, let's count. Now, I see a negative, which means my parent function which would originally look like this. Whoop. Try to draw the answer. My parent function, which would originally look like this, is going to flip. And so it's going to look like a negative slope. For the center 3 dots. Okay, so let's go ahead and plot the actual points here. Okay, so let's do both of these at once with our table. So we're going to times by negative 1/2, 0, minus 1/2, minus 4, and I'm going to leave that one off. I think I'll have enough points. Okay. Now, notice that these values are going to change. So the positive is going to go to negative. So over 1, down 1/2. Over 2. 2 cubed is 8, but half of 8 is 4. 2, 1, 2, 3, 4. Looks as though I could probably make this one fit. So that's going to be 13.5. Over 3, down 13.5. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, just barely. Okay, now I'm going to count the other direction. Now this is a cube parent. So this is the general shape that I'm transforming here. All right? Okay, over 1, up 1/2. Over 2, up 1, 2, 3, 4, and then connect. One thing to look at is these 3 dots here in the center. They look like a minus 1/2 slope. I say look like. This is a curved line. This is not a slope. It just looks like a slope to help us recognize the stretch value that we're using. Okay, let's go ahead and do a second example. Let's mix it up. Let's do y equals negative 2 root x plus 3 plus 2. Okay, let's write down our transformations. Reflect over x. Stretch 2. Left 3, up 2. This right here is going to be our starting point. Okay, notice I say center and starting point. This is a square root, this is a cube. Okay, so my general shape, be a good idea to write that general shape next to the parent. Okay, left 3, up 2. Okay, and I'm going to write my counts down next to it. Okay, you are not memorizing your counts, you are simply doing the parent function. This particular case, my parent is root x. 0, 0 is the start. 1. Square root of 1 is 1. 2, not a perfect square. 3, not a perfect square. 4. Square root of 4 is 2. Square root of 9 is 3. Notice you need to pick the quantities that are going to evaluate to integer coordinates. Okay, now let's count. Okay, we've got the stretch of 2. So I'm going to times by negative 2. Okay, these are going to be my values. So over 1, down 2. Over 2, 4, down 2, 4. Over 4, 5, 6, 7, 8, 9, down 2, 4, 6. And connect. Keep in mind you've got to get, starting point is the point. The other end is the arrow. Remember, we're using your knowledge of transformations to use that a value to stretch it. Your parent function would have looked like this. Notice that the y-coordinates are twice what they would have been compared to the starting line. Okay, so let's go ahead and label this picture with the domain, -3 to positive infinity, and the range, okay, bottom to top, -infinity to +2. Notice infinities have open brackets and the points have closed brackets. Let's go ahead and make this look like. Okay, let's go ahead and do a third example, but this time we're going to look at intersections. So we're going to write an equation that's going to have two sides to it. Now we've done a cube and a square root, so let's do a cube root. Cube root x plus 1, okay, and equals, let's do, this is a little tricky, guys, hold on. Okay, let's make this equal to 1/2 quantity x plus 2 squared minus 1. Now, this is an equation. Notice that it's not y equals, and we would say solve. But we're going to solve graphically, which means we're looking for the x coordinate of the intersections. So our answer is going to be x equals. Okay, so we have two graphs. We're going to assume y1 is cube root x plus 1. So let's go ahead and graph that one, and I'll do it in blue. So this is left 1. That's it. That's the only transformation. So left 1. Okay, so then we're going to write our counts. I'll leave them in blue. 0, 0, 1, 1. Cube rooting. 8, 2. 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Okay. 1, 1. 2, 4, 6, 8. 2. Connect smoothly. Okay, and now I'll go ahead and switch colors, and I'll do it in red. Okay, and we're going to let y2 be the other function on the other side. Okay, so this one is compress 1/2, left 2, down 1, left 2, down 1. Oh, it appears as though we already found one intersection. Okay. So let's go ahead and put our table over. Remember, this is a review parent. So 0, 0, 1, 1. 2 squared, 4. Compressed by 1/2. Okay, so over, up 1/2. Notice that that point is below the blue line. Over 2, up 2. And then we reflect this. And draw your parabola. Okay, conclusion. Right here, -1, -2, -1, 0, 1. The solutions are only the x coordinates because our equation started with x's only. The answer is x's only. All right, let's go ahead and write an equation given a graph. So this would be part 3 of our notes. So I'm going to write the table of values here so that you can plot them. Okay. -4, 0, -4, 1, negative 1, 4, 2, and 9, 5. Okay, and connect. Okay, so I have an endpoint and an arrow. The first thing you need to do is pick out the correct parent and shape. So you have 4 to choose from. Remember, the shape is going to tell you which parent to use. Okay, square root. Pick out your transformation. Ooh, down, 4, stretch, unknown. You might be able to look at the graph and compare the counts. Okay, so I'm going to do that. 1, looks like it's over 1 up 3. So I can guess that the A value is 3. Now, if you're not sure, I'm going to go ahead and show you how to do that algebraically. Okay, so let's set up the equation. Y equals A square root x minus 4. Okay, pick any other point on the curve besides the starting point. So, for example, this one. Plug it in. Negative 1, root 1, minus 4, and solve for A. Oop, A equals 3. And so our equation would be make sure that you are picking the correct parent based on the general shape of the graph. Okay, so the last thing we're going to do is transformations and extension. And we're going to write down a statement here. Okay, and then maybe we'll do a graph, but maybe not. Okay, so the question is, what is the transformation of this graph? So if I wanted, I could graph it. Notice that 49 is a perfect square, but 98 isn't. Also notice that when you have an addition inside a radical, you can't simplify. The only thing that we have taken out of radicals are perfect square factor. And so I'm going to rewrite the inside of this radical in factored form. Now my radical property tells me that when two quantities are multiplied, I can separate them like so. Well, the square root of 49 is 7. Left with root x plus 2 and then a plus 3. And so my transformation is stretch of 7, left 2, down 3. Let's look at one that has a cube root. Y equals cube root negative 8x minus 16. Okay, so I'm looking at my coefficient. At first it's negative under the radical, which I don't want to leave there. And then 8 is a perfect cube. But your radical properties only let you separate if there's multiplication. So I'm going to factor out my perfect cube. And then I'm going to separate. Then I'm going to evaluate. The reasons we would like to be able to do this is so that you can graph it. Okay? We don't do transformations or compressions with the x here. And so we convert it this way. Okay? This would be reflect over x, stretch 2, left 2. Woohoo! We're done. There's the bell.